So so what we saw last time is we developed that we saw that potential energy is a form of stored energy, and we can usually convert potential energy into kinetic energy or another type of stored energy. So we saw two forms of potential energy yesterday. We looked at, that's a crappy color choice. It's all sorts of bad decisions today. We saw that we have gravitational potential energy, which if we have a reference point of the floor equals mgh, right? And we have from equilibrium position for a spring, we have that the potential stored in a spring is 1/2 kx squared. And remember, we were able to introduce Hooke's law yesterday, which is that the force of the springs is with a minus kx. All right, there's some interesting consequences there. Don't lose track of the fact that this is also equal to ma. Newton's law always holds, and again, some interesting stuff happens when we look at spring motion in a whatchamacallit, when we look at spring motion as in terms of a differential equation or second order differential equation. Okay, so we have these ideas here, and of course we want to keep track of, right, is that u, or delta u, the change in potential energy, we defined as minus the integral of f dx, right? And that comes from our statement that delta k equals minus the work. All right, so all of this stuff comes from the definitions of work and things like that. We're sort of putting pieces together to build our structure of energy. All right, and we have here a thought question, and this will help us sort of keep in the signs. It'll help us get us warmed up a little bit. So we have a particle. We have a particle is moving along the x-axis. So in each of these, the particle moves just along the x-axis. All right. And the figure shows three situations in which the x component of that force varies with x. The force has the same maximum magnitude in all three situations. And I want you to rank the situations according to the change in associated potential energy during the particle's motion, with the most positive first. So you want to be careful here, because here you might get bigger numbers, but if they're more negative, they're less than, right? So you want to be careful here. And I want you to look at, we want to rank the situation according to the change in associated potential, all right, according to the particle's motion. And so we have these forces here, right? F1 with these maximum values, okay? So we want to rate each of these. So I want you to look at this and think about those calculus definitions. The point of this checkpoint is to relate these calculus ideas to what you're looking at here physically. So let's see what you guys come up with. So you just want to see which one is associated with the largest change in potential energy. And the only hint I'm going to give you is that in this case, if we have U1, let's say you get UA is equal to 10 joules or minus 10 joules, and VB is equal to 2 joules, or UB, sorry, we would say that UB would outrank UA, okay? Because it would be more positive. So keep that in mind as you go forth. That's the only thing that might not be clear that I want to clarify for you. So instead of doing part A, because once I do part A, it's all true. Once you know how to do this problem, they're all super easy. So let's go. Maybe someone, oh, I'm looking at something here. Okay. So look at it and see if you have any ideas. So my next hint is, how do we describe the integral in calculus? How do we describe it geometrically? Like we describe the derivative as the slope of the tangent line. How do we describe the integral? It's my next hint. The area, gotta be more specific, Joseph. Area under the curve, not the area of the curve, right? But it would be the integral, right? Very good. So if we have a curve, the area under the curve is this curve is described with some function g. The integral of g dx is the area under the curve. These are how Riemannian integrals are defined. Okay? So if we want to know, if we can know that the change in potential energy can be related to an integral, and we have some curves here, and we want to know most positive to negative, which ones are we going to pick? And again, it asks for the most positive first, not, you know. So notice each of these is, okay, good, we've got some stuff coming in. So we've got force curves, right? But look at it, read the question carefully, Artin. See which one is the most positive, not necessarily the largest area. Remember what I said here, VA, if UA, or potential energy A is equal to 10 minus 10 joules, but potential energy B is equal to 2 joules, the 2 is going to be bigger than A because it's more positive, by virtue of it being more positive. So when we look here, all right, so what we want to do, if these are all F's, they all have areas under the curve, right? Which is described by this integral. No, 213 is actually not correct. It's a good guess, but it is an incorrect guess. So let's take a look, and we're actually gonna see. Let's go here. So if we look at this, we have a minus sign. So we'll get areas. So you'll notice A1 and A3 will be equal, but A3 will be positive because you have a negative area here. You have a negative area here, and then you have to multiply it by a negative sign, right? So that will mean that it actually 1 is the most positive, right? And then even though the area for 2 is bigger, now the areas for A1 and A2, these are both going to be negative, but the question is which one is more negative. Now the area for 3 or for 2 is bigger, but it's more negative. So that means we actually get, oh, sorry, 3 is the most positive. I was just looking at that and got 1. So 3, and then 1, and then 2. And I messed up on my comma there. Because remember, one of the hard things to realize, and one of the biggest steps from going from sort of non-scientific thinking to scientific thinking is we don't care about absolute quantities so much as we care about changes in quantities, right? So for instance, when you're looking at temperatures in climate change, you don't care what the temperature reading was, you care about the change in temperature. So the graphs can be confusing to people because there's 0.1, 0.2, 0.3, because you're looking at change, you're looking at more dynamic graphs. And a lot of the intuitive data is not explicit, it's buried, it's a little more subtle. So here we're looking for the associated, the change in the associated potential energy, not the potential energy itself. And we're looking for which change is the most positive and negative, all right, not which has the biggest energy value. So that's the difference. That's what you have to look at. That's what you have to be careful of with these signs. All right. Are there any questions about that one? Does that take a look at it and think about it, because we didn't have we were sort of paused for a while. It's okay. Questions are good. I don't see my microphone thing work. Okay, is it working now? Okay, good. It's working now. All right. But do you all at least see what I mean? Where it's so when I look at this problem, I think it's actually kind of hard to work out when you don't see it. But then once you do see it, it's really simple. Did everyone? I'm just wondering if that's how everyone was sort of feeling about it. Right. No, no. Walter White was a smart, if extremely misguided character. Um, yeah. So I think what I would recommend to you is to marinate with it a little bit, read it, and focus on the words that are important, because reading these problems and interpreting them are really incredibly important. So we know what we want to do. We want to rank the situations, but we want to rank the change in associated potential energy. Don't be afraid to go and highlight these things and look at them, uh, and really sort of marinate with it a little bit. It'll make stuff like this easier. And the more you can compact what I affectionately call as word vomit, and this was a fairly medium word vomity checkpoint, the better you'll get at it. It's good practice. Okay, so now that we've introduced potential energy, we want to expand into our conservation of mechanical energy. Now that we have potential energy and kinetic energy, we can start talking about mechanical energy, which will be fun. So, I'm just debating whether I want to do this on the whiteboard. I want to kind of do this on the whiteboard. So we'll look at the slide here, and you can see what it says, but I want to introduce it as each part and sort of talk about it a little bit. The slide is not working for me here. Okay, so we want to define mechanical energy EMEC as the sum of kinetic energy and potential energy. Okay, so when we talk about any sort of conservation law, all right, this idea of mechanical energy being conserved, it has to do again with that idea of a system, right? When you're an isolated system and things only act within each other in the system, you will find that mechanical energy is conserved, which means that the initial energy is equal to the final energy. All right, so we can expand this. K initial plus U initial equals K final plus U final. All right, and now what I want you to notice is so with this being true, if we move everything to the other side, we can get a very nice expression of our change in our energies in terms of the total energy. So you'll notice if we move everything from the initial side to the final side, we get 0, because we've moved everything over, right? Equals K final minus K initial plus U final minus U initial, right? And then we can see that we get our big result that delta K plus delta U equals 0. And this is the big statement of energy conservation. All right? So that's where we get mathematically. But we really do want to understand that and a way to understand this is if you have a system, right? Say you have a system with 5 joules. Now, in your final version, you'll have to also have 5 joules. That number can't change. But what can change are the individual kinetic energies and potential energies. So for instance, think about you could start off with something like 5 plus 0 equals 4 plus 1, right? You could have 4 plus 1 equals 3 plus 2. You could have, you could even have 6 minus 1 equals 7 minus 2. As long as everything gets to 5, you're okay. All right? And there's an infinite number of ways to get 5. Right? Pick your favorite integer, multiply it by your other favorite integer, or subtract it by another integer, and you can get 5. Subtraction makes all things possible. So that's the key with energy, is what we really see is that while we can say the total system is the same, right? We can see that within the system, things can actually change quite rapidly. And that's what we're really going to study. So let's go back and look at our clean slide again and get a feel for what's going on here with Chapter 8. So let's go and let's look at the fancy equations. So as you can see here, this is just a little cleaner version of what we looked at, and I want to draw what we looked at before. So we had we were able to show in our last slide that delta K plus delta U equals 0, and the implication there, of course, is that delta K equals minus delta U. And so we get this consequence of energy conservation, and we can see that this result by just defining energy conservation and employing it. They'll want to talk about work done by conservative forces and all that stuff, and yeah, you can do that, but this is fine. I think it's more compact and makes sense. And then, of course, they're just using 1s and 2s, and I use finals and initials. And so we want to at least go over this and see if we missed something in an isolated system. Again, remember I said that before. We're only conservative forces. We didn't say that. Cause energy changes. The kinetic energy and potential energy can change, but there's some in mechanical energy of the system cannot change. So that's just what we talked about. The only part we missed was conservative. That's fine. It was sort of implied, but right, if a force is not conservative, there's an energy loss to heat. And we're going to find that total energy is conserved, but when we need to sort of build up that machinery. We're just going to focus on conservation of mechanical energy, and when we're talking about mechanical energy, we're only talking about conservative forces. Okay? So, this is what we found before. It's a very powerful tool, all right? So basically, this is worth saying in bookies, if you will, or Booklish, whatever language you want to add to it. When the mechanical energy is a system of is conserved, we can relate the sum of the kinetic energy and potential energy at one instant to that of another. This is the important part, without considering the intermediate motion and without finding the work done by the forces involved. So we don't need to, when we talked about work and forces, we sort of needed to know what was happening continuously at each and every point. But when we look at energy, we only need snapshots. All we have to do is look at one instant and then the other instant. That's why I wrote that E initial equals E final. And I'll write it again up here. It's worth pointing out. Remember when I wrote on the slide, on the board, E initial equals E final. so that we can see that again. So that is always going to be, that's when energy is conserved, those values stay the same, and it doesn't matter what happened in between. So one application, we can choose the lowest point in a system as the potential energy equals to 0, and then at the highest point of the system, U equals is the maximum value, and it has its minimum kinetic energy value. All right, so basically something we could look at is, if we're looking at, say, a tree, look at Professor Tolan's awesome art skills. Well, isn't that a great tree? And the ground. So usually we call the ground U equals 0. All right, and you always want to pick your lowest point in your system as 0, because otherwise you start getting negative values and things get complicated. So it's a good convention just to always pick it. So like, for instance, in my office right now, right, I have a desk and I have a floor. So it might be tempting, if I'm doing examples with you, to pick the desk as my U equals 0 point, but then I have to contend with the floor. So I might pick the floor as U equals 0. And you might say, well, why not pick the first floor? Well, I'm not really doing things all the way on the ground. So, it's fine. So, you want to be within reason. Now, when you do this, say you have a plank here. All right? So this plank would be U is max. And when you have your maximum potential energy, you'll have a minimum in kinetic energy, right? The more you drop, the faster you get as you go down, the more kinetic energy you pick up. Okay? So that is one way in which we'll solve problems. Now let's take a look at how energy transforms from kinetic to potential in a system such as this. So they're going to look at a system that's a little more complicated. They're going to look at what's called the pendulum. We're not going to really talk about pendulums, but I want to show the motion, so I'm going to stop. I'm going to stop sharing for just a second. So right. So in our previous example, y is maximum at the top. But I want to do this first. So a pendulum, if you can see my pen, goes back and forth like this. And that's the motion we're going to look at in our energy diagram. Now you can see that you'll pick the lowest point in the system, so where it just grazes the pen, as 0, and then the maximum height will be at these where it stops and turns around and comes back. Okay? And we're gonna look at that and see how the energy behaves at each of those points. So let's get back to the file. It's imperfect, but it's okay. All right, so here we can see the pendulum. First, I want to go over the motion, and then we'll go over how the energy changes in that motion. So as we can see, we'll start here at A. The pendulum swings, and it keeps increasing till it reaches a maximum displacement from this equilibrium position. And then you'll notice it starts swinging again until it reaches the other position, and then goes back to the original. So it's that back and forth motion we just saw. All right? Now when we start here, you'll notice at the lowest point, where U is equal to 0, there's no potential energy. So if there's no potential energy, just from, I want to write the thing here. So let's look at K1 plus U1 equals K2 plus U2. So if we know the total energy, right? So say E total equals 5 again, right? Now, when I'm here, I know that both of these sums have to get me to 5, right? But if my U is 0, then I know that my kinetic energy is the maximum, and for the case of our example, would be equal to 5. All right? And now we're going to look, as the pendulum starts swinging, it starts gaining height. So as it increases in height, some of that kinetic energy is turned into potential energy. And when we look at here, it's about half and half, so it's 2.5 and 2.5. Now, energetically, we can understand this, right? As we keep increasing height, we lose more and more kinetic energy. But we can't lose kinetic energy forever. We only have a finite amount. We can only lose that 5 joules. And then we get to a point where the kinetic energy is 0. Now keep in mind, right? Keep in mind that the kinetic energy is equal to 1/2 mv squared. Therefore, if k is 0, v must be 0. All right? So if we have 0 kinetic energy, we have 0 speed. And so we've stopped. And at that point, again, the total energy must be 5, but we have 0 contribution here. All that kinetic energy has turned into potential energy. All right? But now, because what usually happens when we stop, we change direction. All right? This is sometimes called the turning point. And we can see that we're starting to go the other direction, and that potential energy is starting to turn to kinetic energy again. Now, you'll notice the velocity has changed direction, but energetically, we're sort of, we're only dealing with scalars, so we're only getting that scalar information. Okay. But then we note direction not by an individual state, but by whether we can tell which direction we're going, because if we're moving one way, we expect, if we're increasing in height, we'd expect to increase our potential energy, right, which happens up here. But if we're moving towards, which we can see going from B to C, if we're moving, though, back towards the left, then we would expect an increase in kinetic energy, which is what we get down here at D, right? And then we can see again how the energy goes and transfers from kinetic back to potential. The potential peaks again, and then we get right back, and we have a circular loop of the system. The point here is to look at how energy transfers in as the height changes of this pendulum. We're not really ready to look at pendulums yet, but what I want you to point out is, and remember, is that path is independent here too. So we can pick any path we'd like to evaluate the energies. Okay, any questions on this? It's a good question point. Oh, why is Umax at the top? Well, remember, I thought I answered that. Now I realize I didn't understand your question, right? I thought you were talking about the coordinate. So remember that gravitational potential, bad color, delete, or bad spot. Remember that the gravitational potential energy, right? When we pick this spot at the bottom, we pick the lowest spot as right here is U equals 0. That's our convention, right? And UG, gravitational potential energy, equals mgy. So at the top, y top is equal to y max, right? Just by definition, that's pretty intuitive. And when we plug the maximum value of y into our gravitational potential energy, we're going to get the maximum value of our potential energy. Does that make sense? I'm sure I'm not an art major. If only I could draw these straight lines. Okay, good. All right, so if there's no questions on this, we will move forward to some more fun and another checkpoint. Oh, Fatima, yeah.
When the pendulum is at rest, why the kinetic energy is maximum? Because the velocity should be 0. So
you have that just wrong, where I might have misstated it. That's possible. I have to turn up my volume here so I can hear you. So when the velocity is 0, the potential energy is a maximum. The kinetic energy is 0. If you look here, I'm going to change colors just for a minute. If you look here, right, where I just circled, V is equal to 0, and there's no kinetic energy, right? All of the energy is potential. So does that make sense? Does that clarify some things?
yes, I mean, in the first situation, in A.
In
the
A?
pendulum, yes, is at rest.
So the pendulum
it's
is
not moving. Yeah.
So that's where you've picked up on something really important here. The pendulum is moving at A. The pendulum's not at rest A. It's just at this position. It's at its equilibrium position. That's where. So if it were at rest and you were to let it go there, it wouldn't move. But we're assuming it's moving there.
Oh, sorry, because I thought it's at rest, and I was thinking if it's at rest, then V must be 0. Then the kinetic energy must be 0 as well.
And you would be completely right. But in this situation, the pendulum is going back and forth, like the pen here. So we're just taking a snapshot here.
All right, thank you.
It actually has a velocity, which you can see by the velocity vector. Okay?
Yes, thank you.
Good, good. At A, it has the maximum kinetic energy. Right. So at A, it's moving. You'll notice that whenever the particle, so you look at A and E here, I guess this would be. So both times where the particle is moving through its equilibrium point, it has maximum kinetic energy. All right, and that's where its velocity or its speed is the greatest. Its velocity is the greatest too. Okay? Good points. Right, but we're not looking at a falling object here. So that would, what you're talking about would be something like this. And yes, you're at your fastest right before you hit the ground. And in here, I guess it's sort of similar, right? Right before you get to your lowest point, you're moving at the fastest velocity, or at the with the fastest speed. Okay. Kmax is at Vmax. Yes, that's a good way to look at it too, right? So the maximum V you have, or when your maximum velocity implies your maximum speed. Your maximum speed will give you your maximum K, right? That's the largest value it could be. Good. Good, good. All right. Let us move forward in our studies. I think we have a fun example coming up yet. And I want to see if you can, I know we always have a lot of information every lecture, but I want to see if we can sort of synthesize what we've just talked about, and we're going to do a checkpoint. Now, the figure here shows 4 situations, right? One in which an initially stationary block is dropped, and 3 in which the block is allowed to slide down frictionless ramps. All right, so it always starts from 0 here at all of these, and you just let it go. So we want to rank the situations according, so we're another ranking problem, according to the kinetic energy of the block at point B. All right, at this point B. Greatest first, and then B, rank them according to the speed. So which one has the biggest, so which one of these will have, so we just sort of talked about that, right? We saw that, and I want to point that out. We saw that kinetic energy equals 1/2 mv squared. So the one that has the greatest kinetic energy will also have the greatest speed. So my hint to you is that the answer for A is also going to be the answer for B, right? They'll have the same rankings. All right, so let's see what you come up with. We have to think about some stuff from yesterday, and we went over it a little bit today too. And my hint to you here is, remember that in order for mechanical energy to be conserved, right, all the forces acting on it have to be conservative. So think about that. Mm-hmm. Okay. Anyone want to take a stab at it? So Kmax is at Vmax, right? So 1, 2, 3, 4. So, okay. So that's one guess. Is anyone, is there agreement with Artin or disagreement? So you're saying 1 is the greatest, then 2, then 3, then, okay, yeah. Ah, so then we're getting same, all the same. Well, let's take a look. Let us solve our disagreement. So with a conservative force, we can choose any path we want. And we'll notice that in each of these, right, to get to point B, go through the same y value or the same h value, right, height or y. So both of these, the u initial for all of these is equal to m g y. Therefore, when they get to point B and they have a change in y, yes, very good. If the ramp had friction, we would have a non-conservative force, and mechanical energy would not be conserved in this way. Very good. But we are looking at frictionless surfaces. So in this sense, we can look at this and say that each one has the same amount. So when they get to B, they'll all lose the same amount of potential energy, which will translate to them all having the same kinetic energy, right? So K1 will equal K2, will equal K3, will equal K4. And now, of course, because they all have the same kinetic energy and the same mass, they must all have the same speed. Okay? So it's the same for all of them. But yes, if the ramp had friction, this would be a different story and a harder problem. Yeah. Yeah, remember we have to know when friction is included and not included, because not including friction will help us develop tools, but it's also very counterintuitive because, as I said yesterday, friction is everywhere in our lives. So we can see they're all the same, and again, the key there is that there are no non-conservative forces. Okay. So now I want you to try and solve this problem. All right, this is a good problem. It's in the same vein. So the huge advantage of using conservation of energy instead of Newton's laws of motion is that we can jump from the initial state to the final state without considering all of the crazy motion in between. Here's an example. A child of mass m is related from rest at the top of a water slide, released from rest at the top of a water slide at a height of 8.5 meters. So we know that we have the height. Assuming that the slide is frictionless, which is a pretty good assumption if you've ever been on a water slide because there's water on it, find the child's speed at the bottom of the slide. So this should be, so use that mechanical conservation of energy. And I'll remind you of some helpful things. Remember that U is equal to mgh, and K is equal to 1/2 mv squared. These are always good places to start. Now, I've noticed in the last couple years, not the last couple years, it's gotten better, but when I first started teaching physics, I was often surprised at how difficult the energy problems were, much more than the force problems. And I think that's because the math is so much simpler here for the most part. When you do the math, it's all basically algebra. There's no hard mathematics. So a lot of it's tempting to sort of intellectually take off the subject. But setting up the problems is a lot more abstract, right? So this is what I would consider, for instance, a very easy exam question. For this section. So I want you to see if you can do it and make sure you can do it. Because I would, if we were in class writing, I think this would be too easy for an exam, this particular question. So but again, it's about putting the pieces together, understanding when to use energy conservation, how to use energy conservation, and then setting up your problem. Solving it's the last step. It's pretty easy. So see if you can set it up and get that speed at the bottom. It might be. I'm more interested in the setup than the, I'm glad you got something, David. I'm more interested in the setup than the actual thing. First of all, notice that the mass is not given. Is that going to be a problem? David, you should already know the answer if you got 13 meters per second. It won't be a problem, right? Right. You solve for V. So for those of you who may be looking, going, what are those three people doing? So I'm going to say if everyone's getting 12.9 or 13, then that's going to be good. But what's more important, again, is not the final answer, but the process, right? So whenever you start an energy problem like this, you always want to start with conservation of energy, all right? So we know that E final equals E initial. And then we can write this as K final plus U final equals K initial plus U initial. Now we know the child starts from rest, right? So the initial kinetic energy is 0. And we know that the final place is down here, the final position is down here at the water. We can call that 0. So the potential is equal to 0. And then this simplifies in this particular problem to K final equals U initial. And now, because we have those written down, we can see that K final is 1/2 mv final squared equals mgh. All right? Now, we're going to solve some pretty gnarly energy problems in this class. They will not be this simple. So you want to keep track of the finals and the initials and not take anything for granted. You want to develop good habits now. So the m's cancel, right? And we have that vf squared is equal to 2 times g times h, and v final is equal to 2gh to the 1/2 power. Okay? Or the square root of 2gh, if you're more comfortable with that. Okay? So if you want to play around with it, you can take the multiply all that stuff together and take the square root. I'm sure 12.9 or 13 is reasonable. But if it's not, you can argue amongst yourselves. Yeah, Tala. U is the potential energy. Yes, it's the gravitational potential energy. So I should probably write a G up here. Good, no problem. All right. So think about this if this makes sense, and again focus on, and I'm gonna actually go over it again because for those who I think it's helpful to go over it again, so I'm just gonna do it because it's so important for the next 2 chapters and really for the next 4 chapters really. We'll be doing a lot of this energy stuff. So again, the first thing when I'm working on an energy problem, I usually try to identify the energies so I know I'll have kinetic energy, and kinetic energy is always 1/2 mv squared. That's always a good term for it. And if I have gravitational potential energy, it's going to be mgh or mgy, whatever it is. But I know that I can use these so that these are correct. This is important, right? We're not concerned with directions. These are scalar quantities. G is never negative. I tried to beat that out of you, for lack of a better word, in the middle. I told you never ever make G negative. G is never negative. When you're dealing with a vector quantity, you assign it a negative value if it's pointing down. But we're not dealing with vector quantities here. Okay? So now we get into the issue of G being negative. You can run into sign issues. So once we have these here, we then write down energy conservation because we know what we're doing, and it's a little extraneous the amount of steps I'm taking here, but if you practice them, energy problems will always make sense and be straightforward. If you just try to start at this equation, most of you will get lost most of the time, and I'm just speaking from experience. I get lost sometimes if I just try and start from this step. So I mean, because you forget something. So it's helpful to sort of know what you're doing, declare what you're doing, because we're still learning the skill. Write everything down, right? and then read and assess. And what that means is look at the problem. We start from rest, so the initial kinetic energy is 0. We end at the ground, so the final 0 is 0. So it's one thing to see that it's going to be 0, but you want to be sure you understand why each time. And then once you do that, you reduce to this equation, and now you can plug in your terms, which we got down here, and we crossed out the m's, and now we just do some algebra to solve for the speed. All right? This is the part most of you will concentrate on, and it's the least important part. In my mind, once you write this equation down, you are pretty much done. And if you just start with this equation, you're almost, it's very close to writing down the answer of 13 without showing any work, right? This is the important part. This is the interpretation and the thinking. All right, so don't throw it away or take it for granted. And the more you get better at this part, the easier it'll be on this part. Okay? So is it the same magnitude of V if it's free fall? It doesn't make a difference. Right? So what we're saying is we don't care about the path because there's only conservative forces here. So yeah, there's no difference between dropping and going down in the frictionless slide. And you'll find that if if you were to go on a water slide and go right into a concrete wall, you would get pretty injured. If you were to jump off something of 8.5 meters, you would very likely, whatchamacallit, you'd very likely, and went into a pool, so 8.5 meters is like less than about 25 feet. You'd survive that. You'd get a big splash. It'd be fun. But because you're in the water, you also break the surface tension, so that's going to make it hurt less. Also, because since you're in the water, you won't get that big surface tension break. So this might actually be less painful. If you're wondering, well, wait a minute, the water slide would hurt a hell of a lot less than jumping off here. There's more complex stuff going on with the surface tension of the water. All right. So now this is sort of a so actually it's a segue that we'll talk about when we get back from break. We'll take our 15-minute break, and we'll come back around 10 or 11 after. But reading potential energy curves is sort of an aside topic, but it's also where we get to see, a little bit of flavor of very advanced physics, because a lot of advanced physics or intermediate to beginning advanced physics is about reading energy curves and interpreting them, because sometimes you can't picture what's going on, and all you can do is look at the energy curve of a system and then sort of intuit from there what might be going on in the system. So it's a way to look at easily complex systems. So we'll do that, and we'll see that these things, we'll look at these curves, what they look like, but we'll first have to look at the properties of them. And I'll probably create one as we go along in the slides, because you'll notice that the curve doesn't come neutral points, and we can write that. Okay, so I'll be back. I'm gonna go away for a little bit, and we'll come back at around 10 or 11 after. Somewhere between 2:10 and 2:15 we'll start, okay? And I'll leave it recording during that time. I hope someone did the Force Lab project. I hope all of you did the Force Lab project. Well, you're all working on it. Okay. So let's push through. Got our 1 hour left. Last hour is always the hardest hour. Okay. So we want to create these potential energy curves so that we can get a graphical intuition of what's going on. But we first have to see how they're created. So in one dimension, we can see that we can relate the force to the potential energy through this derivative here. All right. And you're going to see something similar like this when you do electrodynamics. But if you look here, we have our we can look at our change in potential related to work, right? Equals the minus of the work equals minus f of x delta x. And then all we do is from there, right? It's not terribly hard. We just we multiply. We can say that f is equal to minus delta u over delta x. Take the limit as x approaches to 0, and you get the derivative. All right. So all simple calculus. And but what we can do though is we can find the force from a plot of the potential energy. So if we actually have u of x, right, we can find the force by just taking the derivative. And we can also, if we have the potential and it's very complicated because we know energy is conserved, right, we can actually obtain information about the kinetic energy as a function of x as well. But there's going to be some features we see in these plots before we get to them. So to find the kinetic energy on one of these plots, we just take the total mechanical energy, right, which will be constant. Let's write that again, that equation up so we can see it again. So again, we're going to keep in mind that k of x equals E mech, which is constant, minus u of x, right? So we can just subtract the u of x part. And in places where k is equal to 0, we're going to call those turning points. And we saw that with our pendulum, right? When k is equal to 0, like right here, it stops and changes direction. So the turning point should make a little bit of sense. The particle changes direction. Remember, k cannot be negative. So at equilibrium points, the slope of u of x is 0, not the value of u of x is equal to 0, but the slope of u of x is equal to 0. So these are places where a particle can be placed and and be in an equilibrium position, right? It'll just stay there. So a particle in neutral equilibrium is stationary with a potential energy only and a net force equal to 0. So if it's displaced to one side slightly, it would remain in its new position. All right, so let's take a look at, there's sort of ways to look at this. So let's look at two situations. We'll call these stable and unstable equilibriums. All right, so imagine you put a little marble at the bottom of the bowl. If you displace the marble from one side, right? If you displace it a little, it'll come back and forth, and it'll eventually come back to rest at this one place, right? You can even make this really stable. You could draw something like this, like a bowl, where it wouldn't move much. It might still be stable there. If you however put the marble up here, any little perturbation or change, one to the left or the right, and the marble is gone, and it's never going to stably come back to this point. It might pass through it, but it's not going to stably come back and rest there. All right, so that's what we mean about stable and unstable equilibriums. And that's what we have here. We just talked about that. And let's take a look at the plots here. And there's a lot to see and a lot to go through. So here we have a plot of potential energy as a position of x. So this is your potential energy curve. All right, now you'll notice that b, you just take the derivative of this plot, and even if you don't have the function, right, you can take the derivative, sort of get an idea, right? So at x2, for example, you know the derivative will be 0. At x3, it will be 0, and at x4. So you'll notice that the force crosses 0 at each of those points. And then you'll notice it gets back to 0 at x5 and beyond. So you can take you can sort of qualitatively take the derivative, right, by looking at the curve points and then taking the second derivative. You know if you have positive or negative curvature, and you can sort of figure it out that way. Okay, so you'll notice like when we go here at 0 and then we drop, we have you know, we go down here, we get x2. So when we take this derivative, this is negative, but then that negative sign out will make this positive, and then vice versa, as we go forth. So we can see that this will be sort of this extreme value of the force, and you can start to do that and put it together. Keep in mind, if you're wondering why it looks backward from what you think it is, keep in mind that force is equal to minus du dt. It is not equal to du dt. Okay? So that's why this negative one, which you might be thinking, well, wait a minute, shouldn't this be a negative slope? Shouldn't I be going down? It is a negative slope, but the negative slope times the negative equals a positive, right? So keep that in mind. Now, if we draw a horizontal line, we can just say, look, they picked my favorite number, right? 5 joules. So we can just say for a 5, so if you only have 5 joules of energy, right? A few things to notice. One, this is not accessible to you. You only have 5 joules. So you'd have to exceed 5 joules in order to get a particle up above this part of the energy hump. All right? And you can see, well, what do they call this? The forbidden region, right? So we can see that for different energy lines, but we can also see that here for equals 5, right? If you're a particle moving, at this point, you would have k equals 0, right? So if k equals 0, this is your turning point. Then you'd move back around and go back. Now, I want you to notice for other energies, right? If we look at other energies, we have some more interesting dynamics. So like for this little green one here, for 1 joule, or yeah, you can only stick to this part of the curve. You can't get out. But if you have 3 joules, well, you can sort of just go from one to the other, but you can't reach this plateau. These are forbidden regions. So basically anything above or beyond, these are forbidden regions. Like the particle can't be past these points in the energy, and these are turning points. Okay? But you'll notice that you can get the kinetic energy by just subtracting the total line, right? That's EMEC minus whatever the potential is. So these potential energy curves give us a lot and can give us physical intuition. They may seem counterintuitive because they're not a bunch of math. I mean, there's math elements to them, but we're not just calculating something and running it through the, running it through the calculation grinder. You actually have to sort of think about the physics of what's going on here. So, anyway, how are we feeling about potential curves? Good? Questions on them? None. Oh, good. All right. Well, let's move ever forward to our checkpoint. Aha, it's like I tricked you. No. So the figure gives a potential energy function, u of x. So we've got a simple potential energy function curve here. Now we want to rank the regions. We have 3 regions here. A, B, so this is region 1, or region A, B, and C. So I'm actually going to write that down to make it a little simpler, because I think it can get confusing with this part here. So let's call this A, B, and C. All right, so those are for each part of the problem, or no, I don't like that anymore. So we'll mark them. Hold on. So let's make them a little more clear. So that's AB, right? BC, but you'll notice BD is this very small region. So hopefully that highlights them a little better and destroys the ambiguity. So we're interested in these 3 regions. Okay, so we want to rank them according to the magnitude of the force on the particle greatest first. So remember here, now here it says the magnitude of the force. All right. So go forth and see if you can figure out what is doing here. All right. We've got CD, AB, BC. CD, AB, BC. All right. Well, let's take a look. Recall that we want to recall that the force is equal to minus du dt. So because, or not dt, sorry, dx. So that means we want to look at and ask for the magnitude. So we want to find the greatest slope, right? So when we look here, we can see that we have 3 slopes. It's pretty obvious that BC would be last, right? Because that's 0. And you can see clearly, you know, there's you can see via inspection that the slope of CD is greater than the slope of AB. So I would agree with all of you that we have CD is first, then AB, then CD. Good. And again, you can do that by inspection. Now B, what is the direction of the force when the particle is in the region AB? So now we're going to focus on this region here. And what direction are we going to go in? Let's see if you can get this. This is a little tricky because there's something implied in this equation which you didn't get. You'll notice that this is not the magnitude. This is a vector. And so we're actually looking at a one-dimensional gradient here. Good. It's positive. It's to the right. Yeah. And because remember, you have a negative slope in A and B, but then you get the negative sign from the derivative, and negative, you know, so this will be this slope is negative times a negative will be a positive, right? So we'll be moving to the right. Very good. Okay. All right. Questions about the checkpoint? Okay. All right. Okay. Oh, that's just our solution. So now we want to talk about, we want to add in friction and start adding in something like that. And look at external forces, right? Because when external forces start acting on our systems, the mechanical energy won't be conserved. But we'll find that if we make our system sufficiently big enough, we'll find that energy is always conserved as long as we can make the system big enough to include what was originally external to now be internal. But let's look at it in terms of this first. So we're going to talk and get into the whole work done by a system, work done on a system argument. So work is energy transferred to or from a system by means of an external force acting on that system. So we can see the system, work is done on the system is positive, work done by the system is negative. All right, and this, you know, these are very sophisticated representations here. But this is sort of a rehash of some Chapter 7 stuff. Now we can extend work on an object to work on a system. So I guess they're trying to say we talked about a system sufficiently enough that they were sure all one and the same, but I suppose they're just very formally extending that work we did on a particle can be worked on an entire system. All right. And for a system of more than one particle, work can change both K and U or other forms of energy in the system. So for a frictionless system, everything remains the same, right? The work done on the system is equal to the change in mechanical energy. And so if there's an external force, that does the work, right? Let's take a look, and this is where energy can get confusing, right? So in the case where energy is conserved, so when delta E mech equals 0, that's a system. There's no internal forces or external forces. There's no force doing work on the system or force, or the system is not exerting force on something external. Everything takes place within the system. It's an isolated system. When we have an external force, the system is no longer isolated. All right. So which means that force can change the mechanical energy to the system, and that force changes mechanical energy of the system by doing work on it. All right. So that's where the work here in a non-isolated system will be equal to the change in mechanical energy. So you want to be careful and keep all these ducks in a row. So delta E mech equals 0 for an isolated system. But now, as we can see in our previous slide, or even here, we have a system here, right? Which is a bowling ball, and a table. If work is done outside, it comes from the outside, the system is no longer isolated. All right? Now, if we add friction to the mix, right, there might be this external force minus the friction, and of course that equals ma, and we can revise a lot of our expression for work, right? So when we look here, we did similar work here to get our force in terms of kinetic quantities that look like kinetic energy, and to get the parts that look like they have work involved in them. So if you solve this for A, like we did before, and you substitute it back in here, you get this equation. All right? And you'll notice you get your delta K, you'll get your delta K again. The reason I'm not writing all of this down is because we've done this once or twice before already. So you get this delta K term, and you get the work term. But now that you have this friction in here, you also get this friction term. All right? And we can see that the work is equal to the change in kinetic energy plus the work done by the kinetic friction force. All right? And we can generalize sort of this whole idea to writing that the work done when we have an external force, right, is the change in mechanical energy, but now with friction we have to add this component. All right? I think it's instructive enough that you should do the details yourself. Again, if you were looking for some specifics on this, I would say go back to our Chapter 7 lectures where we actually do this for the frictionless case, and we derive this equation without 828 without the friction term. All right, you can see how all these substitutions work if you do it that way. So we don't have to redo those. But that should give us a general idea, and what we're going to see is that once we can do that, we will be able to relate the frictional, for a system with friction, we will relate the work done by friction to the change in thermal energy. All right, so this will give us a nice little cleaner expression here where the work is going to be equal to the change in mechanical energy plus the change in thermal energy. All right, and thermal energy comes from the forming and breaking of the welds between the sliding surfaces. So if you play with the force as you're playing with your force lab, right? There's actually one of the activities is a microscopic view of friction, where you can see this actually come into play very readily. All right, and again, you have to remember that you're still taking dot products and things like that here, so you have to be careful about the direction of your displacement versus friction. All right, so let's go forward. I did not want to do this checkpoint specifically. So let's take a look at this example. All right, and let's work on this for a little bit. So a food shipper pushes a wood crate of cabbage, total mass of M equals 14 kilograms, across a concrete floor with a constant horizontal force of 40 newtons, right? So in a straight line displacement of magnitude d equals 0.5 meters. The speed of the crate decreases from v naught, right, equals 0.6 meters per second to v equals 20 meters per second. So you notice we're going to want to work out how much work is done by the force F, and on what system does it do the work. And then we want to know what is the increase in thermal energy of the crate floor. So I want you to try this for about 3 or 4 minutes, okay? And I'm not going to make you volunteer. I just want to give you 3 minutes to work it out. Figure out where you can't get started. And if you can't get started at all, it's okay. Try and push through it for 3 or 4 minutes. Just guess, right? And I won't leave you hanging too long. Just guess and try and do it, and then we'll work through this example. Okay, we'll work through the problem. The point of doing this is, again, because I've seen students struggle with this, I want you to I want you, when we go over it, not to just see me go over it, but to be like, oh, that's what I didn't get, and think about it. And that's all we need to do. You don't need to volunteer what you're not getting, but if you get it all and it makes sense, you can, feel free to say I got the answer, and we'll see if you get that. Okay? So let's give it till 22, right? To work on your own and see what you get. I'll be quiet now so you can work on it. You know, sure. This one or this one? This one? Okay. Mhm. Back to the problem. All right. All right. So it looks like we have an answer for the first part, but again, it wasn't about, and that's great. Good for you, Dan. But again, the point here is to just stop. Don't worry about it right now anymore. Put your pencils down and your thoughts down. And we want to try and let you at least think about where you were confused and see if we can work for it. Because again, answers are great, but methods are better, right? So let's take a look at, there's a lot of stuff given in this problem, right? We're given the force. We're given the force. We're given the displacement. And we're given a speed change, right? V naught and V. So these are the given information. Now, it's often helpful to draw a problem. So the food shipper pushes a wood crate of cabbage across a concrete floor with some horizontal force. So we have our well, hold on, let me, there's enough to clear here. We're going to look at the green border as our floor. So that way I don't have to draw one. And we'll look at the red box as our crate. And we know that a horizontal force, I really wish I could draw straight lines with this thing, with these things, everybody. I do. I'm just gonna draw the regular straight line. I don't want to mess it up. Right? We know that a horizontal force is applied to the box. Okay? So that's the picture. And I find that this can help organize one's thoughts. So let's look at the, we certainly have other stuff going on, like the normal force and the frictional force. But right now, it just asks how much work is done by force F and on what system does it do the work. All right? So let's look here. Now, if we look at this here, we can say work is equal to F dot D, right? And you'll notice the first thing you want to say is, well, where's the displacement vector? It's also along the floor. So we know they're in the same direction. And we can calculate F dot D pretty easily. They're in the same direction, so that will equal 40 times 0.5, which is 20. But the answer, the 20, is the 20 joules is not the whole story, right? We need to figure out, is the on what system does it do the work, right? So is the force doing work on this, you know, is the work being done on the crate, or is the crate doing work? So to determine this, we want to check which energies change. And because the crate speed changes, there is certainly a change in the kinetic energy. And if there's friction between the floor and the crate, which there is, there's going to be a change in thermal energy. So we notice that the force and the velocity are in the same direction, and that's the crate on the crate and the floor. So the system on which the work is done is the crate floor system, because both energy changes occur in that system. All right, so we want to be able to identify this crate floor system. This is where everything changes. Okay, but now we want to look at the increase in thermal energy of the crate and the floor. And this might have been a little more, this one might have been a little more challenging. Now, you might have been tempted to figure out the friction force and everything like that. That's a way to do it, but it's very, very long and roundabout. For B, we can note that the work is equal to the change in mechanical energy hold on, I messed up here. Forgot my E. And we already got the work from part A. And we can remember delta E mech here, right? We notice there's no potential energy. So for this problem, it's going to be equal to just delta K. And I want to point that out. This is one of the reasons I tell you not to memorize a bunch of stuff. This is only true for this problem, right? I've looked, there's no potential energy. I can't find any potential anywhere. Like gravity, it's not moving up or down, so that's not going to matter. There's no spring, and that's the only two potentials we know. So therefore, the potential energy is just always zero. But we will have a change in mechanical energy, which will be equal to our change in kinetic energy. You'll notice we have V naught and V here. So we can write final minus initial. All right, and if we plug that in, I don't know what we get if we plug all that in. Do we have, the mass is equal to 14 kilograms. They gave us that. So you can plug all this in and get a number. So we'll call this delta K. If someone wants to report the number, that's fine. But what we can see now is that delta E thermal is going to equal work minus delta E mech. Or delta K. I already did that. Delta. So we just calculated this number. We have this number from part A, and now we can get the delta E thermal, which is 22.4 J's. That's about right. 22.1, 22.2, depending on how you round, something like that. Okay, so hopefully you were able to figure out, let's go through the problem again. So the first thing we have to realize is that is the system that we're in, or the first thing we want to look at is the work done by the applied force, right? And that was pretty straightforward. We're given the applied force, 20 d, the displacement of half a meter, and that's a pretty simple work computation. Now, figuring out what system does on what system does this force do work? Well, I mean, it's really you're looking for the system of particles. So it's doing work on this, it's connected to the ground, and we can see that work is going to be done externally by friction, right? And so what we can see here is that the system that that's these forces doing work on is this crate floor system. All right, it's just identifying it, but that's all there is to that, right? But you do have to be cognizant of what system you're doing work on. Think of it as like the context of an argument, right? This gives you the context in which the physics is taking place. But then when we do the increase in thermal energy, we want to recall that the work is the sum of the change in the mechanical energy plus the change in the thermal energy. And we leverage that we actually knew the work done, to realize we could calculate the mechanical energy, which in this particular problem is just the change in kinetic energy, right? We have those two velocities above, or speeds rather, and we could calculate delta K, it's just a number. And now we have a number minus a number gives us our change in thermal energy. Okay? So I hope that made sense. think about what you were stuck on. If you got stuck with that problem, I guarantee you it wasn't the math. If you're getting stuck on this problem, it's about figuring out, interpreting what to use. When do I use it? And the only way to get through that sort of fear of solving the problem is to just give it a stab and see if something works. And it's okay if it doesn't work. That's fine. Just come back and try again. Again, the way the chapters are organized, you should be able to zero in on something, right? But again, it tells you what it wants. It says how much work is done by the force F. If you're completely lost, figure out how much lookup work in the index, and you'll see that the definition of work, if you go back to chapter 7, tells you how to calculate how much work force does, and you just do that. When you want to look at the thermal energy, you can go back in your book and find the expression for thermal energy, and you could say, okay, so I had work, wow, I've got that, and then you can think, is there any way to get the mechanical energy? And if you keep going back and forth, you'll eventually, I'm not saying it'll take a small amount of time, but you'll eventually find what you need to solve for, oh, we went too far ahead. You'll find what you need to solve for this change in thermal energy. Okay? So if you just keep plugging away at it, you'll get there. All right. Moving on, we want to talk about the total conservation of energy. All right? And this is sort of the most general form of energy conservation. So energy transferred between systems can always be accounted for, and the law of conservation concerns the total energy of a system. And this includes mechanical, thermal, and other internal energy. And this is actually kind of, will kind of get thrown away here, but it's really quite fascinating. The total energy of a system can change only by amounts of energy that are transferred to or from the system. But considering only energy transfer through work, right? Work is equal to delta E equals the change in mechanical energy plus the change in thermal energy plus the change in internal energy. Now, what I find fascinating about this is that in my mind, the internal stuff and the external stuff are pretty different, and yet they're related. You can relate the change of completely internal processes to completely external changes. That's kind of weird. I mean, think about it. It's not just enough to blindly put numbers in and solve the equations and be like, work is equal to 20 joules, right? There's interesting stuff here. And the fact that you can say something about the external forces acting on a system in terms entirely of the internal elements of the system is pretty fascinating. And I will say this, that conservation of energy is probably the strongest scientific statement I can think of. What I mean by that is in chemistry, biology, and physics, you will learn about the conservation of energy in every class. And the conservation of energy is a principal component behind quantum physics. It's one of the key guiding principles. It's also a key guiding principle in the general theory of relativity. And it's a key component of classical mechanics. So energy conservation is something that no theory can live without, or no model can live without. And it's why, if you ever see those sort of crazy people with their perpetual motion machines, why they're dismissed so easily by many scientists, particularly physicists and engineers, is because all of those require energy conservation to be broken, and energy conservation is one of the best tested theories or ideas, hypotheses in all of science. Every result hinges on it being true. So in order to break it, you have to have something pretty compelling then, just, oh, look at my, I'm misunderstood. So the energy conservation here, what we've arrived at is, it's a small part of what we're learning in this course, but it is the biggest idea we're learning in this course as far as applications to other fields. An isolated system, a truly isolated system, is one for which there can be no external energy transfer. So the total E of an isolated system cannot change. Now there's some fascinating thoughts here, like where finally can you get to an isolated system? One of the more interesting questions people have talked about in philosophy and in physics is the universe a isolated system? And what does that mean if it is and if it's not? So if a lot of in some of the more crazier realms of particle physics, for example, and some of the not so crazy ones, they will, to be honest, they will tell you that if the universe is an isolated system, then its total energy is zero. And there are models in which you can actually have a universe pop up from nothing. As crazy as that might seem, they're actually all pretty consistent with quantum physics and experimental physics. So some crazy stuff, some exciting stuff. That's what we get when we talk about energy. And again, in a completely isolated system, the only energy transfers that happen would be internal to the system, and that might make more sense with this mechanical and thermal energy part being related to the internal energy. Or for two instances of time, you can rewrite it like this. But the point of total energy conservation is to define what is ultimately an isolated system, right? So that's what I sort of alluded to this earlier. You can make if you have a system and you have an external force acting on it, the question is, can you make your system big enough in which you encompass that external force now is within your system, and you now have an isolated system again. And of course, the advantage here is we don't, like we had for mechanical energy, we can relate any two instances of time without considering intermediate energies or times. And that's pretty cool when we're discussing the universe, right? Because you'll know the total amount of energy through the whole thing. So I believe that is, I think we'll talk about power. We talk about a skater pushing away. This is a whole system, right? The skater on the ice with the post. So external forces can act on the system without doing work. Her push on the rail. External forces can act on a system without doing work. Okay, so a force can act on a system. Sure, not all forces do work, right? So a force can act on the system but do no work. So if the skater pushes herself away from the wall, she turns internal kinetic energy in her muscles into kinetic energy. Her K change is caused by the force from the wall, but the wall does not provide her any energy. All right, so that's where we can sort of lock that into the internal argument. And that's just a cute example. What we really want to see is that we can look at we can expand our definition of power. All right, and in general, the power is the rate of energy at which energy is transferred by a force from one type to another. And if delta E is transferred in a time delta t, we of course have the average power and instantaneous power. These now can be expanded to entire systems or isolated systems. But again, within, because the total dE dt of an isolated system should be zero. It should not be able to have any power at all. But individual parts going from one part to the other, little processes that are only part of the system, can certainly have energy changes, right? And then deliver power that way. So that is chapter 8. So we've got a little bit of time. So what I want to do is just introduce the ideas of momentum, and then we can sort of use that as a good launching point for next week. Okie dokie. Chapter 9. All right. So we're going to talk about center of mass and linear momentum. And before we get into momentum, we're going to look at the center of mass. So this is essentially going to allow us, when we talk about chapter 9, so basically when you're talking about quiz 2, center of mass will be on exam 2, and the very basic definitions of momentum. But before we really get here, we want to explore this idea a little bit. And what the center of mass allows us to do is depart from talking about a single particle to a system of particles. And what it does is the center of mass allows us to treat a system of particles as one object. But it can be very counterintuitive. So for example, The center of mass could be at a location where physically none of your particles exist, but you treat your system as if it is one particle at that location. That can be a little weird. We won't start off. The picture here is a lot simpler. You have a bat that's being tossed into the air and rotating, right? So you see this bat rotating, but you'll notice that when you look at the center of mass, if you look at the end of the bat, the path is doing all sorts of weird stuff, right? It's sort of, let's make actually, we could even do that. Let's make a path of this point. So if we were to draw this, it would look like this, right? It doesn't really look like a parabola. It looks a little different. It's a little more complicated. But you'll notice, because it's got this extra rotation part in it, but you'll notice the center of mass, let's clear all this, the center of mass keeps a nice even parabolic motion, right? Through everything. So instead of looking at the bat, we look at one point moving as this center of mass. All the other points in the center of mass, they'll rotate around this point, right? You'll notice that if you look at the points for the bat, right, the head of the bat is even more extreme. If you look at that, right, it's very strange and weird because you're compounding a translation and a rotation there, which is something we'll learn how to do, but not quite yet, not quite at chapter 11. So Pluto and well, actually even the Earth and the Moon. So the Earth and the Moon's center of mass is on neither the Earth or the Moon. Earth and the Sun is different. The center of mass is definitely at the Sun. But the Earth and Moon, it's about 80% to the Moon. But Pluto and Charon, right? Yeah, they rotate around each other. So the center of mass is this special point on the object for which the motion is very simple. Okay, and again, we pick this point because it's the easiest point to analyze. And so, do we sacrifice complete knowledge of the system? Sure, but we can learn enough about the system while keeping our calculations as simple as possible. All right. So, the center of mass of a system of particles, center of mass will be abbreviated COM or COM. But the center of mass of a system of particles is the point that moves as though all of the system's mass were concentrated there and all external forces were applied there. But again, I want to draw a quick system of particles, and it's very important to point out, right, that if that's my system of particles, my center of mass could be right here where there is no particle. And I would apply all the forces at that purple X, even though there's no particle there. That's where this can be extraordinarily counterintuitive. All right? So we have a method of finding the center of mass. So we'll, of course, start off with two particles and make our lives easy. And we'll, you're going to notice that we're looking for a position, right? So sometimes it helps to put a particle. So if we have two particles, where we put the origin matters. So I'll make two. I'm going to make, oh, darn it. My brain is getting ahead of my hand here. Oh no, it took away my points. That is sad. So let's make two red points then. These are our 2 points. Let's really illustrate what we mean here. So I want to make a set of lines with different colors. So you'll notice fundamentally the center of mass is a position. So if it's a position, where you put your origin is going to matter. All right. So we have two origins here. All right. You almost certainly did do something similar to this in Calc 2, except now you're doing it in physics, so it's better. That's just my 2 cents on it. So anyhow, what we are finding a position fundamentally, and so the blue set of axes will describe if one of these points is at the origin, right? So we have this mass here, and if that's true, we can look at the x-centered mass and get this equation. For two arbitrary particles, this will be the equation. Now, I want to start with by developing this equation here. What I want to do today is develop or justify this equation by and then yes, no, I know it does. That's why you have to take Calc 1 in order to take Physics 1. You have to take it before, not with it. So I want to start with this equation and justify this equation, and then I want to derive this equation, okay? Because we all know I like that. So let's start with our purple axes, okay? So we want to find, so if both of these masses, let's make this even simpler. If both of these masses are the same, we would sort of assume that, well, both of these masses are, the center of mass should be in the middle of the system, right, where the origin is. Now, when we look at this formula, we're going to see that in general, XCOM equals the sum of MI XI over the total mass of the system. All right, and this will be our prescription. And you can see that here with two terms. That's exactly what you have. But you'll notice you take this, you look at your position. We're going to call this X1, right? And we're going to call this X2. And what we do to find this XCOM is we look at and we say, okay, MX1 is our first term, plus MX2, M2X2, over the total M is M1 plus M2. So this will be our center of mass, right? And we can sort of see that we have to take into account the distance of one mass away from some point, and the distance from the other to another point. And then again, that x coordinate will depend on where our origin is. All right, so this x1 and y1. Now, you'll notice for two particles separated by some distance d, if one of the particles is at the origin, right, say we put our origin here in the blue one, now the distance, x1, from the origin is 0, because it's at the origin, right? So that means that this term goes away, and you'll notice that they change this x2 to d right there. M2 stays, and you have M1 plus M2. So this equation is simply a special case of this equation. And with that said, this gets a little deeper, a little quicker than I anticipated, and it's something I would want to do all at one time, and this is a perfect review slide to jump into it. This is a great place to sort of start and the best place to stop at this particular point. So I'm going to take the attendance, and I'll stick around until about 3:15, 3:20 or so, and then I'll leave the room. So if you have any questions, let me know. But otherwise, that is it, and have a good weekend. So I'm going to turn my video